All right, good morning. It's 10:20, so we're going to start. So I have some announcements today regarding messages that you will have or should have received from Dr. Brown. And it only pertains to you if you filed an SLGS request, whether you filed it yesterday or at the beginning of the lecture this semester. You should have received an email confirming the accommodations that you've requested and any follow-up discussions or any follow-up actions that need to be taken on your part. Okay. So if you have not received this email, as I mentioned on Monday, that you should have received yesterday, then please let us know. Once again, this only pertains to those who have filed a request. If you have not filed a request, this does not pertain to you, and you don't need to do anything in regards to the exam, okay? Other than actually take your exam. Speaking of the exam, as I've mentioned, there is a practice exam. It is practice in the sense that it emulates the conditions of the real exam 1. We will open it later today, and thus you'll have 7 days before your in-class review. Okay, so please go through it. It is actually timed for 55 minutes. You have unlimited tries, so that once you finish, if you didn't get the correct answer, you'll know that. And so then you have ample time to review, to retake the exam, the practice exam, to come to recitation with questions, to come to office hours with questions, come to your in-class review that's dedicated to reviewing for the exam with questions, and then anything else that you need clarification on. Okay. So we want to give you ample time to simulate the conditions. So even though it's timed, because proctoral cannot be executed without a time limit, it's timed in the same way as your real exam, but you're able to go back and see the answer so that you work out anything that there's any confusion on. Okay. Obviously, with that, not only are you exposed to the types of questions and the style in which we ask these questions on the exam, but it also gives you ample time to practice in the testing environment so that you're familiar and that you're technologically equipped and ready to go, so that we minimize distractions and any technical glitches that can occur that we can control. Okay? And please let us know if there are any issues. There is a dedicated discussion thread for the exam in regards to formatting or anything else that you experience that you have a question on. All right, we posted it on there so that everybody else gets the same answer that you would get. So we're all on the same page. Any questions regarding what I just said? Yes. Yeah. Mm-hmm. And your TA will also work through some of the lengthier calculations so that you know the methodology and that your answer isn't correct just by the sheer fact that it's within some tolerance factor. Now, we've been quite generous with the tolerance factor on the homework, but of course, by us being generous, it has also led to a few cases where someone has submitted the wrong answer via incorrect methodology, but still got it right on the homework. Now, you can go back and make sure that your methodology is correct by just looking at the solution, okay? Now, our tolerance factor isn't so generous that it accepts every answer, but instead of, 0.1% acceptance, maybe we put it at 0.5, and that was generous enough to to allow certain answers through. We've been able to catch those errors, and those individuals have also alerted us that their incorrect answers were accepted once they looked at the solution. So, we have taken that into consideration. On the exam and also in your practice, you'll see in the questions that we'll ask for specific sig figs. So if we're expecting an answer to 3 decimal places, we'll actually ask for that. So there's no confusion of how to round, right? At this point, we want you to be able to understand the methodology as opposed to, you know, figuring out if it's supposed to be 0.02 or 0.002 or whatever the case may be, okay? So that's that. The other thing that may be a pleasant surprise for you is that there's only one question on the exam that's worth your time, in the sense that it counts for a grade. So your exam 1 is out of 100%. You get 5% of that for just doing the practice exam. This is to encourage you to really get started early and become familiarized with the technology. And so the last question asks you whether or not you've read the question and understand the conditions of the exam. So if you answer it, you automatically get 5 out of 100. So then you just have to get 95% more to get 100%. So we're encouraging you to take the practice exam, and this is your incentive right here, okay? So you need to do that, and that's the last question. Obviously, you should do all the questions, but if you wanted to scroll to the end, there is the spoiler alert, okay? And of course, homework is due as usual. You will not have a homework due the week of your exam. We want to give you ample time to focus on reviewing the concepts, discussing it in recitation. There will still be a worksheet though, but you as a class in recitation can decide how you want to balance that time, okay? All right, I see a hand. That is correct, yeah. This is really to incentivize you all to become familiar and get essentially 5 free points on the exam. Unlimited. And 100% is actually answering the last question. That's it. All other questions are worth 0 points. Yeah, so it'll tell you if you got it wrong or not, but it's not worth anything because we want you to keep on practicing, okay? Okay. Let's get started by finishing up mechanical properties. So the last bit of mechanical properties is the discussion of polymers and viscoelastic behavior. And you could tell from the portmanteau that we'll be discussing polymers that sometimes behave like viscous liquids, and sometimes they behave elastically. Okay, so of course that renders these polymers to have some rate dependence on their mechanical properties. This is just a review on some of the terminology that will come across again today. To review, we talked about thermoplastics in the polymer structure module, and these are typically more ductile. There's very little cross-linking. There could be some, but very little. They're linear chains. They could also be branched, but definitely not network, right? And because of this structure, they're typically more amenable to recycling in the sense that we can manipulate the chemistry again to restructure it and reuse the material for another application. And so I've listed here some examples of thermoplastics that are typically recyclable. So you have polyethylene terephthalate or polyethylene as well, low density polyethylene like that of grocery plastic bags. high density polyethylene that you typically find more in, let's say, piping. Another example of pipes, PVC, polyvinyl chloride. Right? Then you have thermosets, which is on the other end of the chemistry of polymers, in which there's more cross-linking and there's more network type structures. And because of this, they're typically more hard and brittle. So the network structure allows them to have a higher yield strength, but to manipulate that and to get the chains to move past each other is quite difficult once they're cross-linked and networked quite a bit. So they tend to be more brittle. And so we'll talk about what happens then at fracture when these materials fail. Right? What do the structures actually look like, and how do the covalent bonds actually start to realign? Okay, if you're breaking any covalent bonds at all. And so here are some examples. Now, the last example, elastomers, vulcanized rubber, we talked about how these chains can actually be cross-linked with sulfur, and that's basically what has made Akron, Ohio, the hotbed of the polymer industry, right? It's because of Goodyear, and Goodyear figured out that you can expose polymers to sulfur, and if you cross-link with sulfur as opposed to carbon, you can vulcanize these materials and strengthen the properties that way. Okay. In the picture that you see here, you typically see thermosets in microelectronic examples, so the blue polymer material that holds a bunch of pins together, right? You want something that's high temperature because obviously electronics can get quite hot. And so if you have these low melting point thermoplastics, your material, your device can actually degrade much more quickly. So you want thermosets as, the casing, or in this case, part of to hold a bunch of pins together for some plug. Okay. So quite useful, but obviously very different type of mechanical properties. In looking at the structure of these materials, let's say you're dealing with thermoplastic. You look at the stress strain curve, and it looks similar to that of the stress strain curve that we talked about for ductile metals. So you have here, the yield strength, and what you see is what we talked about before, where you can have areas that your polymer looks quite amorphous, and that's all these chains right here. And so when you stretch them, the hairpin turns that are the crystalline areas, they start to pull apart from each other. And now you have all these strands that are in the middle, right? So you're applying some stress, right? There's some elongation, and then you continue to do so. And the crystalline region right here, they mostly stay intact in terms of their length. This length right here, most of the time this length is called T. They're elongating, but the amorphous spaghetti-like region is increasing, as you can see here. It's increasing. And then eventually, near fracture, the tensile strength of the material, where it's most maximum, is basically right before fracture, because obviously once it fractures, right, there isn't a strength anymore. So when I say stress at which fractures occur, I really mean right before it fractures. We can measure that number, that value. And what you see is the alignment of the crystalline area relative to the amorphous area is obviously more aligned than it was in the beginning when you had your starting material. And this makes a huge difference in the mechanical properties, because once you align these polymers, you increase their strength in that particular direction. So that's known as drawing, which we'll briefly talk about later, but that's known as drawing. So you can increase the strength of a polymer by just drawing it out. And effectively what you're doing is you're changing the microstructure to something that looks like this, where you're altering how the crystalline and amorphous regions line up with each other. This is particularly useful if you're obviously designing fish line, like fishing line wire, right? You're drawing it out so there's high strength in these materials. You could think about, you know, drawing and extruding for making plastic soda bottles. Those geometries need to be strengthened. Potentially some plastic liners within your aluminum soda cans as well. So one of the reasons why your aluminum soda cans don't corrode is there's actually a plastic liner that's inside that's taking care of the chemistry of the liquid that's in there. Okay, so this is typical stress strain curve for a polymer that's semi-crystalline, linear, or somewhat branch. Okay, no high network or high degree of cross-linking just yet. When you do have a lot of cross-linking, it typically looks like this, right? Where you have a lot of covalent bonds, you have linking in between the chains. So what happens then as you get to near failure with these brittle materials? You can see that there's some elongation, so these bonds look a little bit longer, but that's about it. The chains are elongated, but that's about it because they fail pretty quickly, but their strength is much higher than that of let's say a thermoplastic that's over here. Okay, so these materials are really designed to be high strength, but cannot withstand a lot of strain. And then you have a special class of polymers called elastomers. Interestingly, you can have elastomers that are thermoplastic as well as thermosets. But mechanically, what's happening with elastomers is they'll start out something like this, you know, there's some amorphous regions, their chains are just kind of, you know, wonky like this, mostly spaghetti-like is how most people describe it as. And then in this region, they start to uncoil and align like so. So they're still cross-linked, it's just now they're elongated and aligned. And what you can do actually is you can elongate this to, let's say, 400% strain, 1,000%, I mean, some ridiculous amount of strain. And that's what you see with rubber bands, right? These type of polymers, you can really stretch them out and they'll actually go back to how they were, right? Like hair ties are the same way, elastic bands are the same way, right? You can stretch them well beyond what you can stretch, let's say, you know, the elastic region of metals. We've talked about 0.002 strain or 0.2% strain, right? Now we're talking about like 400, 500, 600% strain. So we're orders of magnitude different in terms of how much strain we can put into these types of elastomers and still get them back. So elastically deform them, hence elastomers. We can elastically deform them to some ridiculously high amount of strain and still get back the structure that we had in the initial state. Okay, so that's why rubber bands act the way they do, right? So if you applied and measured the tensile strength of a rubber band, it would look something like this. So then you ask yourself, okay, well, is that the entire curve, the elastic region? And basically it is. It doesn't behave in the same way as metals or ceramics, right? It's a whole different regime. So basically we say, okay, it's all elastic and there's really no plastic deformation because that's going to occur when you snap the rubber band, basically, right? Now, over time, that rubber band, if you keep on stretching it, over time you deform it and apply some stress, that's different than just a one-time deal, right? We're talking about strain rates over time. That's much different than just saying, okay, I'll stretch it once and then it'll go back. If you keep deforming a material, eventually its stress state, initial stress state is not going to be the same. And we've seen that a little bit with metals where you can apply some stress to plastic deformation and then you release this, you know, the load, and it'll come back and recover some elastic strain, but now your stress state is a little bit, your initial stress is different than what you started with, okay? So to jog your memory, for like a metal, if you apply some stress to deformation, release the load, you get back, it will recover some elastic strain, but then let's say you apply the load again, it will continue, but its initial stress, its initial strain, excuse me, is not going to be the same. Okay. So two different cases is all I'm saying. Now, we get to something that has both elastic behavior and viscous liquid behavior. And it depends on your rate, your stress rate, right? So I brought here silly putty, which I've mentioned before, and I anticipate that most of you have played with silly putty at one point in your life, given statistically it's a common toy. So maybe that's a safe assumption. But basically, so what has happened was at the beginning of class, I made these into balls, and they've sat here during the entire lecture up until now. And what has happened is the silly putty has gone from this to this, okay? And let me switch real fast because I think it may be better to show it on here. Okay, so you can see the dimension, it's much flatter than its initial state. So it was once a ball about 20 minutes ago, and now it looks, you know, something like this. So obviously it has sort of relaxed. So what I mean by how the mechanical behavior of viscoelastic materials, you can see that if this is your initial state, this ball, and then over time it has flattened out, it behaves sort of like a viscous liquid, right? You anticipate when you pour molasses that it sort of slowly spreads out. So that's more of a viscous state, right? But if I get this silly putty to be a little bit more spherical, then you could see that it behaves a little bit more elastic in this case, right? It's not slowly responding to what I just did to it, which is bounce it, F equals MA, right? And GH. So you can see that it behaves a little bit more, it behaves more plastically depending on the rate of the stress. So then we need to talk about this material in that context. What rate are we talking about when we talk about the viscoelastic materials? So here in this example, what we can think about is if we apply a load at some time 0, right? There's no load. And then at some time TA, we apply some load instantaneously. So you can see the load just increases like a step function. And then let's say we keep that load for a while, and then then the material is allowed to relax. Okay. Well, for an elastic response, the strain remains the same. So you see here, the strain plateaus out, right? There's no change in the strain. If it's a viscous material, the strain linearly increases, as you see here. But a viscoelastic material, what happens is there's no load, and then there's an instantaneous strain, and that will change over the time, and then there will be some relaxation in the strain once you release the load. Okay. So it looks like some combination of the two, some viscous behavior and some elastic behavior, and it's time dependent, right? So when I bounce the ball, that's a very short amount of time versus when I just let the silly putty sit on the table as I lecture. So what's happening in these polymers is that in terms of the change in the volume of the material, unlike metals where upon melting you have, you know, some volume that's in the liquid state, and then at the melting point there's a drastic change, right? And then you have crystallization and there's some volume change there, but it's quite dramatic, the change in the volume for, let's say, a crystal. For a polymer, what happens is it, you know, the volume is in some liquid state, it has a melting point just as crystals do, but then there's a gradual change here. So it's not so precipitous, right? It's not like this huge change in volume. You have some gradual change in the volume, and then it sort of never melts really. And so we call that the glass transition temperature. So it's in a glassy state at TG and beyond in terms of being a lower volume, lower temperature. So it never really crystallizes. And so when polymers, you know, discuss their materials, one of the important parameters typically that's discussed is TG, right? And you can probe this value in a number of ways through DSC, differential scanning calorimetry. So you can track the heat flow, and basically you can pinpoint some TG. Okay. Now, upon relaxation, we need to talk about the modulus of elasticity, right? We've seen this for metals. We've seen this for ceramics. We can also talk about modulus of elasticity for polymers as well. And so what happens is here you apply some strain, some constant, you know, the strain is constant, but here the stress changes over time. So it's sigma of T, right? So it's T dependent. So thus the modulus of elasticity, E of T, right? Before we just said it's E. It's in the linear region, rise over run. You know, it's pretty simple, Y equals mx. But now over time, the modulus of elasticity changes for this material. So we need to know what is the stress at that time T divided by the initial strain. Okay. And that initial strain is the strain that is right here. So this instantaneous strain. Before you apply the load, there was no strain. That's not your E0. Your E0 is this instantaneous strain that occurs when you apply the load. Okay. So different polymers behave differently in the sense that if you have just amorphous polystyrene, it looks something like the green curve, where your relaxation modulus changes as a function of temperature. That's the x-axis here. If you have cross-linked atactic type material, it never really crystallizes, and so the relaxation modulus just sort of plateaus out, right? Atasticity is when the functional groups are on randomly everywhere. Okay. And then crystalline isotactic polymer. So isotactic means all the functional groups are on the same side, so they pack better, they crystallize better. It behaves like the red curve that you see there. Okay. So just by looking at the relaxation modulus, you can get a sense of the chemistry before you even probe the chemistry and the microstructure of the material. Okay, so here we have an example of some polymer with an initial stress of 3.5 MPa, right? And so we know that sigma naught then is 3.5 MPa. And we're asked to calculate the relaxation modulus E at 10. So after 10 seconds, what is the relaxation modulus for this polymer if the stress is 0.5 MPa after 30 seconds, right? And so we know these stress at time t divided by the initial stress is equal to the expression given here, where T is the amount of time that has elapsed and tau is the relaxation time. Okay. So we can take the log of both sides. And what we want to know is, what is tau? Okay. So we know that tau is so now we know that we can have some values that we can solve for. So after 30 seconds, sigma of 30 is 0.5 MPa, but it initially was 3.5 MPa. So we can solve for this, the relaxation time. So who wants to plug into their calculator or computer and figure this out? What was the value? Someone shouted out a number. What is tau? Okay, so 15.4 seconds. Okay, that's your relaxation time. So now we can say, okay, well, if it takes 15.4 seconds to relax, then I can calculate what my stress is at 10 seconds, because I have the relationship of this. Let me be clear with my unit so that there's no confusion. This is not a 5, this is 10 seconds. Okay, so sigma naught, my initial stress was 3.5 MPa, so I can plug that in. And if I solve this, I get 1.83 MPa as the stress after 10 seconds. And so then I can calculate what the relaxation modulus is. The measured strain instantaneously when it was pulled in tension is 0.5. And so basically I'm just doubling. Okay. So because it's time dependent, you need to know the stress at each time. So if 8 seconds has passed, you need to calculate what t equals 8 seconds is. Okay. If 5 seconds have passed, you need to know what the stress is at 5 seconds. Right? Here it was for 10 seconds. Okay. Any questions on this? Okay. So the last bit is just hardness. We've talked about many mechanical properties. We've talked about elasticity, ductility, yield strength, tensile strength, stress at fracture, toughness, and now we're going to talk about hardness, and it's the resistance to indentation, right? It's difficult to indent diamond, so we use it to cut other material, or tungsten carbide. So these high hardness values, what it means to you is that it's resistant to cracking, resistant to wear, It's typically high strength. It's also a good estimate of the tensile strength. They correlate, but they're not linearly, they don't linearly map onto each other. And the test is pretty simple. You take a standardized stainless steel ball and you drop it at a certain height and you measure these values. It also used to be that you could take material of different hardness values and you could also scratch whatever it is that you're testing. And if it's resistant to that, then it's harder than whatever material you had. So you used to lug around like a little box of just known hardness, materials with known hardness. Obviously, that's very qualitative, but you can do now standard hardness measurements. And so in your book, it discusses several standard ones, and they can be converted from one system to another by some multiplication factor. One of the more common ones is the Brinell hardness testing. So basically, you take a standardized sphere, could be 10 millimeters, and you drop it on your material. So the stainless steel ball is, some diameter, capital D. The indentation that it makes, if you assume spherical model, then you could also measure what the diameter of the indentation is, or small d, and then you just calculate based on that the Brinell hardness factor, and that's it. And the tensile strength is just about 3.45 times the number that you calculate by just dropping this ball and measuring the indentation. So it's pretty straightforward. Obviously, it deforms your material, and most likely, you don't want to use that same area, but it does give you a sense of what the hardness is. Okay. So that's just a brief aside there on hardness and mechanical properties. So, design factors. If we have all this information in front of us, and we've done the stress strain curve measurements, we've done all this, how do we actually use it to design for a specific application? So here's an example where we take into account the safety factor, or factor of safety N. What that means is we over-engineer, right? If we know the load that a material needs to withstand in a certain application in service, what we typically do is we'll say, okay, the factor of safety is X. Let's say it's 4. If that's the case, then we multiply the force by 4, and then we know, okay, how big in terms of the diameter does this material need to be, right? So if you're designing some gauge cable, right, what is the minimum diameter it needs to be if you're going to apply a certain load in tension to this cable, right? So over time, we get better. We don't have to over-engineer as much. The Brooklyn Bridge, if you've ever gone there, or if you're from Brooklyn, it's like massively over-engineered, right? The amount of support that this bridge has is absolutely unnecessary, but it was built so long ago that there are some measurements and calculations now that we can do to predict failure that wasn't available then. So what do? You just overly engineer massively. So this range is affected by what is the end use. If maybe it's a fishing line, maybe your design factor could be a little bit lower, like 1.2. So you lose a fish because your line snaps, Unless you're in the wilderness and you're really relying on that one fish for dinner, not the end of the world, all right? Maybe you can forage some leaves, I don't know. If this cable is holding up people in a ski, on a ski lift or something like that, obviously the design factor is going to be more. And of course you take other things into account, but this explains why you have a range for your design factors and how much you have to over-engineer for certain applications. Yes, question? I did not know that. Thank you for that tidbit. Yeah, I mean, that certainly is true. When people design certain projects, you do build smaller models. And that happens, you know, bridges, it happens with parks for accessibility, things like that. So anyway, landscaping is a whole nother, you know, beast that I won't go into, but that does wrap up this portion of mechanical properties. So, oh, hold on. So I'm going to exit out of this and and we'll go over to deformation. So we can talk a lot about mechanical properties. Oh, in case you're curious, the ball that I just showed you in about 15 minutes, it also has deflated. We talked a lot about mechanical properties. Now we want to talk about deformation's effects to the mechanical properties of the pristine material, and how do we also strengthen materials once we know, the initial property. So we'll talk about how these deformations propagate that affect your property. It could decrease your strength, it could increase your strength, it could decrease your ductility or increase your ductility, right? And that affects how the material will be used eventually. We'll talk about how deformations occur. They occur through slip, and so that's dislocation movement in single crystalline materials as well as polycrystalline materials. Why isn't slip important in materials that are not metals, right? And so ceramics and polymers, they don't have slip systems for this mechanism of deformation to occur. And strengthening, how do we actually use it to our advantage in strengthening materials by impeding dislocation, say? And then how do we get rid of these dislocations once we have them? Let's say a material is worked, right? How do you get it back to its pristine state? How do we anneal, and at what temperature, things like that. So to review, when we talk about dislocations, we're talking about line defects, okay? Before, we talked about point defects, vacancies, chemical impurities, for better or for worse. Not all defects are bad, obviously. Interstitials. Now we're going to talk about dislocations and actually how it interfaces surface or 2D defects such as grain boundaries and external surfaces. And of course, this will also lead to defects in the volume, such as cracks and voids, but that will come in a little bit. So in strengthening materials, we really want to look at dislocations and how to impede them and what will impede them. Will grain boundaries impede dislocations? Yes. Will putting in another atom impede dislocation? Also yes, right? Grain refinement, will that impede dislocation? Also yes. So all these strategies revolve around dislocations. So when we were talking about edge dislocations, we were talking about how they move. So as you remember, here is the half plane that has now shown up in your material. It's an extra half plane. And the way it propagates upon a shear force, you can see this way. Okay, this way. You could see that it doesn't just actually like instantaneously shift, right? It's not like you move the whole plane and now it's over here. It shifts pretty gradually. And so you could see the half plane now moves here. What has happened is these bonds are being broken and they're being reformed here. And then it propagates again. The bonds that were here, right, are broken. And now they're formed over here. And so on and so forth, until it gets, let's say, to the other edge, if it makes it there, okay? Or to the edge of a grain, say. So your end material looks something like this when it started out like this. And so you have this moving dislocation over time. So when that happens, when you have this edge dislocation, your material will feel the compression in this region where the half plane is, and tension in an area where there's more space. Okay. And so as this dislocation is propagating, if it sees another dislocation, they'll actually repel each other because you have this compressive force and another compressive force, and that's highly unfavorable. So they'll actually repel each other and stop. The other thing that could happen is, let's say you have this compressive stress that's here and the tension down here. As it starts to propagate, if it sees dislocation of the opposite sign, so here your compression is up here, your compression is now down here. As these two line defects approach each other, they can actually form a perfect crystal again, because in one case you had an extra half plane up here, and then in the other case you have an extra half plane down here. If you bring them together, they actually align, and now you have a new plane, but it's perfectly aligned, and mathematically it looks like the rest of the crystal. So you can actually annihilate dislocations by bringing two opposite dislocations together. Okay. And so what do you mean by bringing dislocations together? Dislocations move. Atoms move, right? If you increase temperature, there's been a lot of transmission electron microscopy that's been done, and also scanning electron microscopy that's been done to show that we can track, we can see in the microscope these lines, these dislocations, and when they move, this is how they behave. Okay. And so that is this example here. So do you see those lines of dislocations when they come to this part right here? They actually can be annihilated or stopped, right? And we can actually measure the angle of these dislocations in the single crystal throughout the experiment. So this is actually really neat, and it's actually more than neat. It's technologically advanced to be able to see the dislocations move and how we can pin them over time. I think we can also play this video. So here, this student is basically blowing bubbles. These are just bubble rafts. Okay, so they're just bubbles on top of a liquid. And that's all there is to it. Do you see how it mimics dislocation movement? So here, okay, it goes very fast. You might want to watch this at like 0.5 x, but basically you can see if those bubbles are atoms, you can see how they move and how here, so you can have atoms shift over time. And this is just bubble. I think the most impressive part of this video is the uniformity in the bubbles. Do you know how difficult it is to blow uniform bubbles like that? I mean, it looked like she was just pipetting it out. I mean, it didn't look like it was a robot, so I'm actually very impressed for that sheer fact. Less so, I mean, these bubble wrap videos have been around since like the 50s. But the fact that she can get this uniform is actually really impressive. But that's, so here you see a point defect, right? So you can mimic this, so you can disrupt the material, and then it will just reform and repack, because energetically, that's what the material wants to do, right? It wants to resolve all those dangling bonds and such. Okay, so one can watch this like all day, but we must move on. Okay, so we talked about dislocation moving. In which direction are they going to move? Well, we have a nomenclature for that. We have a system of describing the dislocation movement, and it is called a slip system, right? That means they occur on the highest packed plane, highest density plane, and along the directions around that plane. So an example would be for PCC, we don't have high density planes, but we do have a closed path high density direction, and that's through the body diagonal. Okay, so here through the body diagonal, the atoms are touching there. So the plane in which that occurs is the 110 plane. And so we can describe that as the family of 110 planes, or curly bracket. And the direction is the family of the 111 direction. So as you recall, one direction is bracket, family is angle bracket, a plane is parentheses, and a family of the same plane is the curly bracket notation. Okay, so these slip systems tell us which plane and which direction it's easiest to dislocate, right? They're going to move, which direction will require the least amount of force to move the atom. And that's typically in the highest density planes or the highest density direction. And so when we talk about the planes and the direction, that is the slip system. And the equivalent planes and directions will be the slip system. And so you can have equivalent. So you can work it out where you can have the 111 plane. So actually the notation should be 111 here for this particular plane, as you worked out in chapter 3 module. And the direction is along here, here, and here. Okay, so combined, this is a slip system, and there's 12 equivalent systems. So you can think about 1, 1, bar 1, 1, bar 1, bar 1, right? So you can think about all the equivalent planes and the equivalent directions, and that gets you to 12 systems for FCC, right? 111 plane is the highest packed plane, and this is the direction that it can move along that plane. Okay. And this is all worked out for you. So in your book, you should see, you know, for FCC systems, the planes as well as the directions and how many equivalent systems there are. For BCC type materials, that's also worked out in terms of the number of planes and directions. HCP is also given, even though we've mostly talked about cubic systems. So we won't talk about the slip planes in the slip systems in HCP materials for this course. So that is a notation. When you talk about a slip system, you must provide a plane and you must provide a direction. And if you have more slip systems, your material is going to be easier to deform. Okay. With that, I'm going to leave it here for next time when we talk about critical resolve shear stress and when it's not perfectly orthogonal to your slip system. See you Friday.